Hello, everyone. Welcome to this Windpower Engineering and Development webinar, Blade Maintenance, Observations from the Field, and Practical Solutions. I'm your host, Michelle Froese, Senior Editor of Windpower Engineering and Development magazine. Thank you so much for joining us. Just a brief agenda before I introduce our speakers. This webinar will be available at windpowerengineering.com. A link to it and the slides will be emailed to everyone who has registered. And at the end of the presentation, we'll have a brief question and answer session. Now you will see several boxes on your desktop, all of which can be moved around to suit your preferences. Initially, the Q&A box is at the lower left, and this is where you can type your questions. I'd suggest not waiting until the end of the presentations, however. Type your questions in as they come to you, and we'll try to answer as many as possible before our time is up. Another box to note is the additional resources initially at the lower right-hand corner of your desktop. These resources are for your information needs. Of course, not everyone that wanted to attend today's webinar could be here, but you can help them learn from it by tweeting key points and the takeaways that you think are important. There is a place to tweet on your desktop, and just be sure to include the hashtag WindWebinar. Now, let me tell you a little bit about our speakers. Today we have three gentlemen joining us. First up, we have John Salmon, Technical Services Manager for EDF Renewable Services. Prior to this role, he served for 2 years as Operations Manager for EDF and 3 years as Field Engineering Manager and Technical Training Manager. Before stepping into the wind industry in 2009, John worked in a variety of design, manufacturing, and process engineering management roles in the semiconductor, hydraulic crane, service truck, and biofuels industries. He has degrees in materials science and mechanical engineering from the University of California, Berkeley, and he is a professional engineer in Iowa, where he resides. You'll also hear from Kelly Miller, who has been in the wind industry for over 6 years. In his current position, Kelly coordinates and oversees blade management and repair services for EDF Renewable Services. He recently transferred from Operation Manager at the Thumb Wind Parks, and before joining EDF, also spent 4 years with Nordics, starting as a service technician in Pennsylvania. He was quickly promoted to lead technician and then to site lead in his hometown of Ithaca, Michigan. This was the same project where Kelly began his work in the wind industry as development officer for the Beep Community Wind Farm. Kelly also has a strong background in construction, where he previously owned and operated his own business for more than 10 years. And last but not least, today you'll hear from Matt Sagala, a technical specialist for EDF Renewable Services, where he focuses on composite technical support, such as blade inspection and repair activities. Prior to this role, Matt worked for 2 years as an advanced wind technician for EDF. And before moving into the wind industry, Matt worked in aviation as an A&P mechanic and composite technician, where he maintained a fleet of 35 aircraft. So with that, let us begin. John, I believe you're going to start us off today. The microphone is yours.
Thank you very much. Good morning, everyone, or afternoon, depending on where you are. I'm going to kick us off and spend some time talking about some of the blade trends and concepts that may be useful in talking about blade maintenance. And then I'll pass the speakership over to Kelly and Matt, who will follow up with some more specific aspects of blade services. A little bit about EDF Renewable Services. We bring to the industry about 30 years of company experience in renewable energy. We are the largest third-party provider of operation and maintenance services in North America, and we offer operations and maintenance, balance of plant, scheduled and unscheduled maintenance, blade inspections, blade repair, and asset management services. We currently have approximately 410 technicians and supervisors in the field, and we provide solutions that are customized to your specific project's needs. And we're very proud that we have a company culture that is focused on safety, and the inset chart there actually shows our improvement and excellent safety performance over the last 11 years. and showing how effective we've been at working through that. This shows our incidence rates as well as our DARTs, and very positive progression on those. In terms of our size, we actually operate over 10 gigawatts of renewable energy. We've developed almost 8 gigawatts, and we have an installed capacity over 4. And you can see there on the map, which doesn't show every site, of course, but it shows, it represents that we're in most states with a variety of wind and solar. We also have some operations in southern Mexico, as well as in Canada, Quebec, and Ontario. So we're quite diverse, and this chart actually shows not only wind, but also the solar and biomass and biogas facilities that we operate. Just talking a little bit about some blade trends in the industry. Obviously, turbines are getting larger. The turbine power ratings are increasing. Therefore, the rotors are increasing to catch more and more power. The implications of that on blades are that we have longer and heavier blades. Those blades are working harder, and so therefore there's increased structural loading, and that loading and the stresses from that can lead to higher maintenance costs. The other major trend worth considering is looking at the wind cost of energy. Obviously, we're applying the least amount of blade material to blades to get the work done to make it a cost-effective proposal as far as a wind turbine goes. The design factors are going lower. There's not as much margin, and that leads to higher maintenance costs as well. The number of owners that we see are seeking blade maintenance services is increasing, and there's a couple of reasons for that. I think in general, the industry is becoming more and more aware that blades do need attention. There's blade problems. They're not going to last the life of the turbine without some very responsible maintenance. And with the age of megawatt blades that are flexible comes more issues, I guess I'd say, more maintenance challenges. So why is blade maintenance important? We have to make sure that the blade structure is not degraded. It's very important to retain the airfoil shape that the blade was designed to have, and for the very reason that if not, there will be annual energy production losses, and so you will suffer, frankly, a loss of revenue because of that. Repair costs increase nonlinear as degradation progresses. That's a mouthful, but what is meant there is that if you allow the blade problems or erosion to continue, that maintenance it's not proportional to how long you wait. You're actually going to pay a lot more to get that blade restored to its best operating condition the longer you wait. And then, of course, if maintenance goes, if you go too long without maintenance, you could actually suffer a complete blade loss. So maintenance factors. One key point is that blade degradation, the rate of blade degradation actually varies greatly site to site, and the reasons for that are many. But there's quite a difference in the density and type of airborne erosive particles that are out there, whether it be water, ice, sand, or dust, or all of the above. How much lightning you get in terms of frequency and intensity. Moisture ingestion, or basically the blade moisture ingressing into the blade and it being absorbed by the blade. Freeze and thaw cycles with their well-known expansion stresses can be degrading. And then also consider that the blade design and manufacture is quite different. There's many different blades out there. They have different erosion properties. They may or may not come with leading edge protection. Adhesive properties and processing, those vary, as well as the workmanship involved. All of these factors can play into how much blade degradation you have and therefore how much maintenance is required and the rate of that maintenance. Things to consider. There should be an established blade and site maintenance plan. Perform inspections early and often. From my perspective, without other considerations, it's wonderful to have a complete all blades on site inspected. Actually, your first day of operation, and then soon after to understand what kind of maintenance rate you're going to need to really handle that well. But of course, then maybe opposing that is that the owner always has a budget. He has financial considerations, and we can't do everything. And so there has to be a balance struck with that. But the more and the earlier those happen, the better. Also consider provider capabilities, the techniques used in inspection, and we'll be getting into more of that. The database to organize collected blade data, and the reason for that is that there's many images. You're looking at a lot of surface for defects, etc. So there's a huge need to organize all of that data, and then of course coming out of that, maintenance and repair planning. So an inspection approach or approaches, the industry has multiple different inspection techniques, putting the customer in control of their solution. Blade maintenance needs can change. Here again, the turbine age, whether it's new, just out of construction, or 10 years in. The condition of the turbines, how much maintenance has been done before and how much they've been affected. The climate, the customer budget, and the blade design. Things to consider, the mode of inspection, just as a few, visual inspections, binoculars, cameras, technicians on the blade, and drones. And all of those can be used effectively. Some, in my opinion, are more effective than others, but there's also cost and timeliness considerations, and so it's always a decision how to most effectively perform the inspections. Your inspection should have the ability to see fine details, and that involves how well you can resolve the image. The image effects you have, you're looking at, for the most part, a very white, large white surface. So your ability to manipulate that image, and some of those effects are useful in terms of contrast or brightness, and the ability to zoom in and out to look at large areas, and then also look at the fine details of an area. And then also consider cost and productivity inspections. The three aspects that really need to happen to have a good maintenance plan: inspection, data management, and reporting. Just a comment or some comments about these pictures. The topmost picture there shows our ground-based robotic inspection, and kind of demonstrates how it scans the blade surface automatically. And then the lower picture, actually, if you can see that well, depending on how large your screen is a fly on a blade that I guess wanted to be part of the inspection. So that concludes my portion of the presentation, and I'd like to now introduce and roll the presentation to Kelly Miller, who will talk some more about our inspections.
All right. Well, thank you, John. Good morning, everyone. I'm going to be providing more details on the inspection process itself and covering the different types of inspections. The basic visual inspection. A visual inspection is completed using binoculars on a high-powered or high-powered optics. A technician will scan each blade and note damage to report to the customer. The visual inspection is the lowest cost option and typically included in O&M contracts because it is required in most maintenance manuals. A photographic inspection is performed by trained technicians using a high-resolution camera and a large telephoto lens. The inspection provides the customer with greater detail of the damage at the site. These types of photos are very helpful in strategic repair plans by the customer. Technicians on the blade. In this technique, technicians perform inspections by positioning themselves directly on the blade using ropes, cranes, or a platform. This puts the technician in a direct contact with the blade to take pictures and more specific notes of the damage to report to the customer. Unmanned aerial vehicle. The unmanned aerial vehicle is more commonly referred to as a drone. Drones can be flown into position so it can closely maneuver itself to the blade to take pictures or a video of each blade. Once the data is collected, the technician then analyzes the data and produces a report to the customer. Mosaic image mapping. In this, more referred to as the cornice inspection. These inspections are performed with high-resolution cameras equipped with a telephoto lens. These cameras are mounted on a robotic arm that maps each blade. The photos are then uploaded and digitally stitched together to form a mosaic image of the blade. The owners are able to view the entire blade in one photo with the ability to zoom in and see the finest detail. Data management reporting capabilities. Basic reporting. A basic report may include photographs of the damaged areas, may include recommendations that can be made to the customer on possible repair and conditions of their blades. Reports are in a PDF form and submitted to the customer in paper or email to the customer. And individual paper reports make it difficult to show the yearly damage progression of the blade conditions. Databases. They provide a central location for sites to store the blade reports from year to year. It's difficult to know each damage progression, however, provides an overview of the site blade conditions. Databases provide the ability for customers to store large quantity of pictures for each blade in their fleet. Files can be stored on the computer and set up to be accessed online. The industry is moving more towards web-based sites, databases. This includes online 24 access to the customers, stores photos that may include mosaic map images in one place for easy access. Customers can easily see damage progression from year to year, and it provides the ability to filter and search photos or damages. Customers can produce fleet blade reports at ease to list all fleet damages. Now Matt Segalo is going to dive into the blade damages and explain those in detail.
All right, thanks, Kelly. So these are the common blade failures with what we see in industry-wise. The majority of lightning strikes, leading edge erosion, laminate delamination, and moisture ingestion. Your moisture ingestion, has a lot of cause with the lightning strikes, causing tip blowouts and such, and also has a cause with freeze and thaw cycles. And then we do have the occurrences with manufacturer defects, such as shear webs and spark cap debonds. So moving along to lightning damage, kind of a process of what we do within EDF to do a repair. We always tell the customer, as in, this is what the picture looks like, but the damage will always most likely be larger after we do remove the gel coat. And this, as you can see in the first picture, we'll remove the gel coat and do some non-destructional testing, such as a tap test to search for more delamination or debonds. Moving on to the second picture, the full exposed damage has been exposed. We prep, insert, new laminate, and also a PER glue to repair the crack. Going on to your third slide, or your third picture, that's after the repaired laminate has cured. We cure everything under vacuum and heat. And then after, adding the filler and such, you add your gel coat and LEP is applied to the leading edge. So kind of in a nutshell, kind of what we do with lightning damage. That's, a fairly minor lightning strike. So with lightning damage, like we discussed, it's unique in every case. Each lightning damage it's not the same. It can be pretty minor, or it can range up to pretty extensive stuff. Debonding of shear webs and spark caps and such. So we have our specially trained technicians to test and repair the lightning system, because also with your lightning damage, you also are looking at your LPS that needs to be tested to see if it's been blown out, and if it has been blown out, then that's an additional repair you have to add to the list. And also repairing and replacing lightning protection receptor, usual case that's pretty blown out, and we have to reinsert a new puck at that point. Delamination also occurs with lightning damage. Like I said, it's pretty unique per case. And then also disbonds. Same thing. It's you can either have some disbonds within spar caps and shear webs and spars. So with leading edge erosion, it's pretty baseline. If you let it go long enough, you start seeing your bond line to erode faster than the original material. So that's one of the things. We go in and repair the bond line first, and then start building back up fiberglass on each side of the pressure side and the suction side. And then what we like to see within the company is replace the gel coat with a leading edge protection, either a roll-on application or a film application, and we usually leave that up to the customer on what they prefer. With both, there is factors that we have to include, such as moisture, humidity, and dew points and stuff like that for the roll-on application, where we don't see that with a film application. So the cost of not repairing. These are pretty unique pictures because you actually do have the tape application on the leading edge, except for the 4 inches or so on the tip of the blade. You can see in each picture the progression of leading edge erosion where there is no protection. And with leading edge erosion, it doesn't take a lot to get things going. Mostly when you start inducing rain and dust and sand, it starts to erode pretty fast. So you can see where the erosion on the third picture has progressed in a large area, and then it's actually starting to peel back the leading edge tape. So if the cost of not repairing, over time, blade repair costs increase, repair costs increase non-linearly as degradation progresses. Erosion can cause significant AEP reductions. So these are some of the numbers we pulled from 3M. Pits and gouges reduce AEP up to 4%, or from 4% up to 10%, and neglect of delamination reduces AEP up to 20%. So those are pretty big numbers when you start looking at entire parks that are 7, 8 years old with leading edge erosion and such like that. So I guess we lead it over to any questions.
Excellent. Thank you so much, gentlemen. That was very informative. So yes, let's take some questions from the audience now. First up, let's see. If a wind farm has had several similar blade failures, how should one go about determining if more blades might be affected or by the same issue at a wind farm? I think this might relate back to John's first presentation. But I'll let you guys decide who could best answer that.
Sure, I can at least start the discussion. I guess it really depends on the specific failure you're talking about. I mean, if there's blade failures due to lightning, of course, all the blades should be inspected to understand if there's been lightning damage. If you're talking about blade failures due to erosion, then I would be concerned that there is a great concern about your other blades, and those should again be inspected. I guess inspect. You've got to know the state of these blades, and the fact that you have failures on some blades is an indication, or at least a concern that the other blades are experiencing it too. There are defects in blades that could lead to failures, and those could be more random and non-existent in the other blades, but you really need to ascertain that.
For sure. Another question, I think for you, John, is why is moisture ingestion a problem, and why aren't blades waterproof? I imagine that would be the ideal world.
Oh, well, they're intended to be, and they start out being waterproof. They have typically a top coat on them that is very moisture resistant. But obviously, that's sort of the point of this whole discussion, is that these blades require maintenance, and that top coat can break down either through cracking or erosion or whatever. And the moisture then, of course, has a path to the internal part of the blade, and that is a problem for a couple of reasons. It can be absorbed by the blade material, the composite matrix, and that can lead to some degradation. It can also lead to, if there's a lot of water in the blade, it can actually throw the weight distribution of the blade off, which is a problem. And of course, it's a problem in winter climates to have that water inside the blade that's now freezing and expanding and then thawing, and so you're getting a cyclic stress in the blades. And then lastly, if there's water in the blade and then you are struck by lightning, or the blade is struck by lightning, you basically have the opportunity for that blade to explode, basically, because you've got superheated steam, and which obviously can create huge internal pressures within the blade. The blade's not ready to withstand that, and it can literally blow apart.
So from water to ice, do ice shedding activities or operating with ice on blades have a negative effect on the lifespan of a blade, and what might those be?
I'll try this first, and then maybe Matt or Kelly can add to it if they've got some more experience on that. As far as the ice shedding process, I mean, it is definitely a problem to operate, or a concern to operate the blade with ice on it, and for a couple of reasons. Number one, that blade, that airfoil shape is not what it's supposed to be, so you're off the power curve basically, and you're not going to be producing as you intend to with that blade. And probably even worse is that that blade unfortunately isn't on there uniformly, so that blade and your rotor is potentially greatly off balance. So you've got a rotor imbalance, and which is very hard on all the drivetrain parts because you've got eccentric loading. As far as the actual act of ice shedding, I'll be honest, I don't have any direct experience or knowledge of that causing a problem to the blades. It certainly causes a huge safety issue for individuals under the blades. It also can be a potential problem for any equipment below the blades as they are exposed to tons of ice being dropped on it.
Thank you. So next, what is the leading cause of erosion, and are there preventative actions to preserve the blade surfaces from erosion?
Yeah, I'll take that one.
Thanks.
So from recent studies, I guess, listening to industry-wise, that, moisture and rain is your biggest leading cause to erosion other than dust and sand particles. And I guess to prevent wise is either, get an LEP application, directly out of the factory when you're, building a park, or start, looking into applying an LEP into the early years of the blade just to have a preventative maintenance. I know a lot of these turbines that we're working on now is that, it's a sleeping giant, that we're trying to catch up to now. And with that, we have to, the costs go up because you have to do the actual leading edge repair damage. And then after you do the repair, then you have the man hours to actually apply the LEP, either if it's, the roll-on application or the tape application.
Great, thank you. Into lightning now. How do you determine if lightning protection system, if it works during an expected strike? And have you ever seen an instance where damage occurred during a strike due to a failure of the lightning protection system?
Yeah, so you test the LPS system with a Mager and really long leads. And it's, you're just basically making out the blade. You connect at the root of the blade and you work down to each lightning receptor. And you make out each receptor until you find a bad one, or if they all are good. But yeah, there is plenty of occurrences where LPS systems have failed, and I believe that comes down to poor design in the manufacturer, where the actual LPS rod was leaning against the pressure side of the blade, and path of least resistance is shot out of in the center of the blade instead of going to the conductor. So it caused some severe damage there.
So is there a way afterwards then to ensure the lightning protection system is viable after an event?
Yeah, so after the event, it goes back to your LPS testing with the Mager. Right. So you repair the LPS and then you retest it before you start doing your laminate damage repairs and such. But at the same time, these LPS systems are only designed to withstand a certain amount of lightning current. So it's kind of one of those things that the force majeure usually ends up with the manufacturer when you're trying to get warranty repair.
Right. So this leads us to drones. So how often have drones or UAVs been used in inspection? I imagine they're becoming a lot more common now. Have you found that it's a more cost-efficient option?
I can start this response. Yeah, drones are a very popular, or UAVs, I think they're also called, is a very popular inspection method, and I guess it's really not an inspection method. It's really just the carrier for the camera. So it's an alternative method to performing a camera inspection. They are popular. It gets you up close to the blade, which is a plus. Maybe counter forces against that against the UAVs is that. Now you've got the challenges of operating, maintaining, and licensing the UAV for operation, and you've got the FAA to deal with. So it's really a choice of what gets you the image. What you're really after is the image. It doesn't matter how you get the image, but you want the best image possible. And I know, speaking for EDF Renewable Services, we're very happy with our ground-based inspections because we have a very, very well-engineered system that performs those inspections.
That's great. Can one of you please address the relationship between AEP losses and maintenance? Can you explain that?
Sure. If I'll go the other way. If you don't maintain your blade, let's pick on erosion again. That's the best example. Erosion, basically, you can look at erosion as altering your airfoil shape of the blade. The blade was designed to have to catch wind using an airfoil shape, and that involves how airflow actually flows over the blade. Once you alter that, and in an inconsistent way, by the way, but once that is altered, you're basically causing turbulence, and that airflow has changed. So there's a lot of field information on this that erosion, an eroded blade will see a degradation or an AEP loss in the order of, we've heard up to 20%, but there's numbers 4%, 10% out there that it can be affected.
Right. And this might seem obvious, but can you explain why larger rotors result in higher maintenance costs? Is there not more done beforehand to kind of prevent potential damage down the line?
Oh, I'm sure that I'm going to make the assumption that the OEMs are doing everything they can for that blade design and manufacture to avoid any negative impact to the blade, and will therefore reduce maintenance costs. But they've got some big challenges. First of all, those larger blades have more surface area, and obviously, so there's more that can be eroded and more that can be impacted. There's also, back to the blade trends that I mentioned early in the presentation. There's some real challenges in terms of cost, so they're trying to do more with less, basically. The loading is going higher on the blades, which can lead to cracking. It can there could be structural issues that happen. There's just not as much design margin on those blades. There's a greater challenge with larger and larger blades.
Are a lot of the issues that you're seeing mainly due to environmental and weather conditions, or do you see a lot of blade problems due to vibration?
Yeah, I'd say the majority of our repairs that we're seeing is due to Mother Nature-wise, as far as erosions and lightning strikes. I haven't seen a lot of cases within our company with vibration issues.
Okay. That's okay. And I have one last question for you. You gentlemen have been great today. Thank you. Has the monitoring of strain or load in blades, is that now used more often in the prevention process and in maintenance plans, or is that something that's looked at now ahead of time as a potential to help later on down the road?
I guess that's a fairly recent development, and frankly, in the fleet of blades that we're operating, we're not seeing that yet. It is there. It is coming. There's technologies that are monitoring the strain and therefore the stress in the blades. So yes, I see it as something that could be very helpful in detecting any negative change, in particular of the structure or the balance of the blade early on. But because I think it is just being rolled out, it's something that we don't have experience with yet.
Right. Okay. And I will ask you actually just one more question. If you have any information or research in field blade failure, and if people are interested, where can they look for that?
Boy, offhand, I don't have a good answer for that. Where to go for blade field failure?
Okay. Well, thank you, gentlemen. I appreciate your time. Anyone else wanted to answer, or we're good? All right. Well, we are at the end of our allotted time for today, ladies and gentlemen. Once again, this webcast will be available for reviewing at windpowerengineering.com. One final message, you can follow Windpower Engineering on Facebook, Twitter, and LinkedIn. I'd like to thank John, Kelly, and Matt for their fine presentations and everyone else for their attention today. From the staff here at Windpower Engineering and Development and from the team at EDF Renewable Services, we wish you all a good and productive day. Thank you so much.